Let's continue on from where we left off in the matrix chain multiplication problem. And to do a really quick review, the idea was that we have a series of matrices of different sizes, n of these, and we want to minimize the number of scalar multiplications. And we know how to do matrix multiplication. And if you have 3 matrices, then this is the number of scalar multiplications required. That depends on the size of the two matrices. We've defined a sequence of dimensions which go along with the n matrices. And then you saw an example where you actually saw that depending on how you do the parenthesization, how you actually do the multiplication, either A1, A2 first or A2, A3 first, it can make a huge difference. Okay, so 7,500 scalar multiplication versus 10 times as many, okay, just by changing the order in which the multiplication is being done. And we said, well, what if we try to do an exhaustive solution? And with this exponential solution to the number of possible parenthesizations for n matrices, and that is omega to actually, that's the minimum complexity. And then we looked at what if we can try dynamic programming. And for the first question is, of course, can we show that it has an optimal substructure? And we spent some time doing this, and we showed that based on the following equation, we can show that, yes, it does have an optimal substructure. And then we also asked the next question, does it have overlapping subproblems? And we also saw that it does have overlapping subproblems. And finally, based on the optimal substructure, we were able to see if that we were able to sort of understand a recursive equation for solving this problem. Okay, so this is where we ended. So let me repeat this recursive solution, which basically said that if we did a split, so we defined Mij to be the minimum number of scalar multiplications need to compute the matrix Ai through J. Okay, so we're going from Ai through Aj. And this is the notation we're using for that, Ai colon J. And we're saying, well, what if we split it up? We put the parentheses between AK and AK plus 1. Okay, so we selecting some integer k, and we're saying, well, we're going to split up the matrix multiplications into the first half and the second half. The first half comprises of all the multiplication of Ai through AK, and the second half comprises of AK plus 1 through Aj. Okay, and these, as you can hopefully see, will have the end result of this multiplication will have a size, a matrix size of Pi minus 1. So this is Pi. So this matrix is Pi minus 1 by Pk. This is Pi minus 1 by Pi. And the last matrix is Pk minus 1 times Pk. And so when you multiply these, you get Pi minus 1 times Pk. Okay, so that's the size of the left half of the parentheses, and the right half is going from AK plus 1. So it's going to be Pk times Pj. Okay, so these are the two end product matrices after you multiplied this whole set of matrices. Okay, and so then the question was, what will Mij be? It does have an optimal substructure, so we can define Mij in terms of its two subparts. Okay, so to compute the minimum number of scalar multiplications to compute the left side is simply going to be Mj by definition, okay, because that's also optimal. And the right side will simply also be Mk plus 1 through J, okay, based on the indices that we've picked. But there's going to be, in addition, there's going to be a cost, right? And that cost is to compute the multiplication of these two submatrices, okay? And that we know is if you have a multiplication of two matrices, pi minus 1 by pk times pk times pj. So the number of scalar multiplications will be based on pi minus 1, pk, and pj. Okay. So basically what is to do this entire product can be divided up into doing the scalar multiplications for a smaller problem. Okay, so it's sort of like it reminds you what? I mean, if we go back to some, well before dynamic programming, when we were looking at quick sort and merge sort, it seems like a divide and conquer, right? So you've divided up into two problems and you're conquering it. However, there is a major difference, okay? That you need to actually look at all possible solutions over here. They have overlapping subproblems. So it's not like quick sort or merge sort where you could simply compute those independently and come up with the result. You can't do that over here. So there are overlapping subproblems, and so it's not. So you have to have a dynamic programming approach to solving this problem, and you have to evaluate, well, for which k value is this actually the best? Okay, because there are a whole bunch of k values, and k can go all the way from pi. Okay, you can go from all the way from I all the way up to j. Right, so we have to look at compute all of those quantities and then select the minimum one. Okay, so which is what essentially the dynamic programming approach says. Well, sorry, the recursive solution says that, well, when I is equal to j, then the minimum number of scale multiplications is clearly 0. But otherwise, you have to look at all possible values of k, from k going from I to j, and compute this value. Okay, so it does have a recursive part to it, and then it does have three numbers which have to be multiplied, and so you will find a whole bunch of solutions. And the recursive solution, of course, is not ideal unless you do memoization, right? So that's what dynamic programming does. It says, well, let's take a look at the solution, and we're going to try to memoize rather these optimal solutions to the smaller problems, working bottom up. Okay, so the next question, can we now figure out how to actually do it? Okay, so how do we create tables or matrices where this bottom up approach can be implemented? So that is, you've seen enough of these problems, you can sort of get a hang of how to construct your own table. Okay, sometimes they have these fancy triangular look as opposed to just a regular square look. Let me see if there's a problem with the internet. I think looks okay. So so here we're going to represent the i's and j's in the following manner. Okay, because we're not going to go through all the values of I and j. Okay, it's just going to compute a subset or half of this rectangular structure, which is sort of shown in a triangular manner, which last time. Okay, so essentially we're going to have an initialization part. Okay, and then we're going to have an iterative loop, which actually comprises of three nested loops for L, for I, and then for k. Okay, so as I mentioned last time, whenever you have this, it's always a good idea to tabulate. Okay, to create your results and do it step by step. Otherwise, if you try to do it, on scrap paper or in the corner of your margins, that's not going to work with problems. So it's a good idea to create a nice little table and look at all the possible values and try to compute it manually. Okay, if you ever had to implement this, then this is what I would strongly recommend, is that you do a few iterations manually, you then implement that in the program, and then you compare the manual results with the automated results, and at least check for certain cases, all right, the boundary cases and so on. I don't think we're going to ask you to implement this. It's not in this course. So let's take a look at what happens when you do the initialization. Well, the initialization is simply saying we're going to set the values for MII. Okay, and that clearly is 0 because this is simply saying what is this number of scalar multiplications required to compute A11, which is essentially A1. Okay, so these are all going to be set to 0. So that is the first step. The second step is to do the looping, and I'm going to do it in different stages. So I'm going to start with the smallest value of L. So L is equal to 2. All right. And L is going from 2 to N. So N in this case is 6. So we're going to have 2, 3, and so on. And I'm just going to do a few iterations, few examples just to show you what the structure looks like. So for L is equal to 2, I is going to go from 1 to 6 minus 2 plus 1. So that's 6, 4 plus 1, 5. So I is going to go all the way up to the 5. Okay, so we're going to do a few of these. J is going to be equal to I plus L. So I plus L, that's 3 minus 1, that's 2. So J is going so J is going, so J is 2 now, all right? And K is going to go from I, okay, I is equal to 1, and it's going to go up to J minus 1, which is 1. So essentially, this entire loop, in the first case for L is equal to 2, you're just going to have a single entry, okay? And if you look at the single entry over here, which is 1 to 2, so we're basically computing Mij, so M12 is being computed, and which is basically the cost of computing A1, A2, okay? So M12 corresponds to computing the number of scalar multiplications to compute A1, A2, okay? So that should be fairly straightforward. It says that's M11 plus M22, both of these are 0, and then P0, P1, P2. Okay, so that's simply to multiply A1 times A2, which is simply this particular value. Okay, I'm not showing the values over here, I'm just showing you the range, which is basically 1 and 2. Okay, similarly, as I becomes 2, now you're going from go from 2 to 3, so we're going to compute this particular value, and that's simply the value to compute A2, 3, A2 times A3. Okay, and you go all the way up till A5 times A6. And each one of those are fairly obvious. A2 times A3 would simply be P1 times P2 times P3, and so on. Okay, so that's all that this first level is doing, where L is equal to 2. So that's not too interesting. Now things become go up the layers. Okay, so essentially, this is where we're going. We're going up the layers, and L is starting from 1 to 2, and so on. So let's take a look at when L is equal to 2. Okay, now let's do L is equal to 3. And internet is not stable. So let me just double check that, see what's going on there. Well, it's on my Android AP, so I can't do better than that. I guess even the Android is feeling the pressure of getting to the end of the semester. Okay, so so let's take a look at what happens when you're trying to calculate L is equal to 3. So I'm not going to go through the actual algorithm which was shown earlier, but I'm just going to show you how it actually works out. So let's take a look at this. So basically what it's going to do is now I and J are separated by 1. So now earlier we were doing 1, 2, 2, 3. Now we're going to do 1, 2, 3. Okay, in other words, we're going to say, well, what's the minimum number of scalar multiplications to do A1, A2, and A3. Okay, that's what A13 means. Now, A1, 2, 3 can be done in two possible ways, right? We can either do A2, A3 first and multiply by A1, or we can do A1, A2 first and then multiply by A3, which we've already seen. Okay, several examples of. And so this would be represented by A2 times A3 is something that we've already done. Okay, so the solution over here is the first one corresponds to doing A2 times A3 first, okay, which is M23, and multiplying it by M11, which is simply 0, because that's simply the cost of computing A1. The cost of computing A2 times A3 is something which we've already done, right? A2 times A3, we've already done this, so we already have that result saved. And where is it? It's right over here. Okay, so A23 is right over here. And then we're going to also figure out what's the cost of multiplying M23 with A1. Okay, and that is where P0, P1, P3 comes in. Now notice that it's not P0, P1, it's not contiguous, it's P0, P1, P3. Okay, that corresponds to P0, P1, P3 to multiply this matrix with the result of these two matrices. Okay, so you've seen how we're trying to figure out which one of these is minimum. So we're going with different values of k. We're putting the parentheses initially at k is equal to 1, and then we're putting the parentheses at k is equal to 2. Okay, so we're changing the of the boundary between the two divided problems. The second problem is where we're choosing the second one, which is where the boundary is now set at k is equal to 2. And so we're going to compute M12, okay, which is basically what's the minimum scale of multiplications to compute A1, A2. Okay, now have we solved this problem already? Well, yes, we have solved this problem already. Okay, so we simply need to, we don't have to repeat that calculation. We can simply use the memoized results from the past, and we can compute 1, 3 based on the results of 1, 2 and 2, 3. And now we have to pick the smaller of the two. But we're not just going to take the results of these two individually and compare them. We're going to take the results of these two, add another product, which is the product, which is to say, what's the cost of taking this, and the multiplication. We've only got this result saved and this result saved, but we don't have the result of multiplying those two matrices saved, right? So we have to do some computation at every level. So, we're going to do this. We're going to compare. We're going to take this multiplied by this product. We're going to take this multiplied by this product and then compare. Okay. So after we've compared it, which I'm not showing you, but it'll be seen later on because this example is directly from CLRS. It turns out that k is equal to 1. Okay, k is equal to 1 is actually a better solution. So the first one where k is equal to 1, this is k is equal to 2. So this one turns out to be a better solution. Now we have to also keep track of which particular value was the best, right? And that's where another table comes in, which is the S table. Okay, and if you go back into the actual algorithm, you'll see that the S table is also being used over here, which remembers the index, which was the minimum of all the values of k. All right. So we're going to store k is equal to 1 over here. That simply says that when we looked at these two solutions, we found the first one where k is equal to 1 to be the better one. Okay. And similarly, you're going to remember which one of those boundaries was the best. Okay, and you can see that if you're going between 5 and 6, the boundary could either be 5 or it could be 6, right? So, and then let's take a look at another example. So this is also given in CLRS. So this is an example where you're looking at this particular value. Okay, so we went up to this level, and now we're going to next compute, take a look at this L is equal to 4 value. Okay, so let's just do a single one of these. So M25 is going to be the minimum of, well, there are 3 possible ways that you can do A2 to A5, right? So you're trying to compute A2, A3, A4, and A5, right? That's what M2, 5 indicates. You're trying to compute the minimum possible multiplications to multiply the matrix A2 all the way up to A5, okay? And so now that problem can be broken down into 3 possible ways of doing the parenthesizations, okay? So you could either do A2, A3 times A4, A5, okay? So compute this, and then multiply these together. Or you could say, well, let's do A2 and then multiply it with the result of A3, A4, A5. And similarly, you could put the parentheses over here, which is A2, A3, A4 is being done first, and then A5, okay? And for each one of these cases, you're going to be able to use a memoized result, okay? So M22 corresponds to this value over here, okay? So that's already been computed. M35 corresponds to this value. So you see that there are pairs. These red values are pairs, and they're being compared in pairs. So you're going to compare 2235 plus this product. You want to calculate it. So you can see that M22 is 0. M35 has been calculated for you. And P1, P2, P5 is being calculated here based on this particular set of dimensions. And it so happens that this particular scenario is actually turns out to be the minimum cost. Okay, so you're comparing 3 results and you're picking the smallest one. So this particular one is the smallest, and this happens where the boundary is actually k is equal to 3. Okay, so the boundary is where A3 and A4 are being split up. So we memorize the result, which is k is equal to 3 is the best particular solution for calculating M2 through 5. And similarly, you can see that these are in pairs. So M24 and M55. So M24 and M55. So again, these are pairs. And the blue ones are in pairs. So that's what's also been shown in CLRS. So in case you want to look at the book, you're most welcome to do that. But if there are any more details generally in the book, that's not really important. My lectures hopefully should be sufficient in terms of the depth to which you need to go through a particular algorithm. The depth that I'm expecting is the depth to which I'm going over in the lectures. Okay. Example for M25, and so ultimately you compute the entire matrix as you're going from L is equal to 2 all the way up till L is equal to 5. Okay, so that's what we saw, that L will go all the way up to 5. And so as you're going upwards, you have perhaps less calculations to be done, or maybe not, you have more calculations to be done. But you eventually get to the apex of this particular pyramid. Okay, so once you've done that, and of course, we're not going to go through the calculations here, but the question is, how do you now, based on the M table, given the M table and the S table, can you now construct the actual solution? Now, this is a question for you. So what is the actual solution? And what were you looking for in the solution? So whenever we have these kinds of problems, we generally have a pair of solutions, right? So if you're looking for the shortest distance between X to Y, you're looking for the actual shortest value of the distance. Plus, you also need to know what the actual route is, right? There's sort of a pair of solutions in all of these. So the pair of solutions come from each one of those 2 tables. So can somebody just sort of point out where the solutions are? It's kind of obvious in one case. Yes? That would be M1, 6, because that simply says that this is the minimum cost to multiply all the matrices from 1 through 6. So that's kind of obvious, right? Now, what about the S table? Tell us how to construct, how to do the actual multiplications, which order should you do the multiplications. So can we look at that and say, well, here is the order in which you're supposed to do the multiplications. Now remember, we're saving the value of k, the boundary point. So based on what I said earlier, so here we said, well, the first example was, we said, well, at this particular juncture, we selected k is equal to 1. Okay. Next, we said that at this particular juncture, when we're trying to make a decision over here, we selected the corresponding value in the S table, and we split the values between from 2 till 5. So if you're trying to compute A2, A3, A4, A5, A4 and A5, then we split it up at this point where k is equal to 3. Okay. So now can somebody tell me what is the final parenthesization sequence? Where do we start from? Start bottom up or top down? So think about this problem over here. So here we're saying that, let's say that this is the problem we're trying to solve. Well, we need to divide it up at k is equal to 3. Okay. And then we can perhaps tackle the problem, do A1, A2. And the solution for A1, A2 would be over here. Okay, A1, A2. And that would say, well, split it up at k is equal to 1. Okay. So so those are several hints. Yes, Shivraj. So you're looking at this particular entry over here, okay? Because we're saying, well, in order to split between 1 to 6 and 1 through 6, we need to split at k is equal to 3. So we're going to put a parentheses over here. Yeah. Yeah. So we put the parentheses around A1. So this is the next level of making up the problem. Okay, keep going. Yeah. Yeah, so k is equal to 5. And so we put the parentheses over here. Okay. So that basically gives you the solution. If you're doing A2 to 3, you can also check that, but that's kind of obvious. A2 to 3 would be at A2. Okay. And there's just two matrices need to, that's kind of obvious. There's only one way to apply them. So that's essentially the solution for the matrix chain multiplication. You have, we went through the whole series of efforts, going through the optimal substructure, then finding a recursive solution, and then taking a look at the recursive solution and saying, well, does it have overlapping subproblems, finding a recursive solution, and then taking the recursive solution and doing memoization. Okay, so there's like 4 or 5 steps that you need to do in every dynamic programming problem. Okay, is what is the complexity? So time versus space, time complexity versus space complexity. So it should be kind of obvious. We've got a loop over here for L is equal to 2, then for I is equal to 1, and then for K is equal to I. We've got 3 nested loops, and without going into too much detail, it basically comes out to be a triple nested loop, and the maximum would be, because it's going from, and the size is n, so it comes out to be n cube. Okay. What about in terms of space? So now, how much space are we using? That is also kind of obvious. Somebody want to state the obvious? Yeah. N squared, yeah. So that's going to be n squared because we're simply using two tables, each one of them being n, actually half of that. All right, so time and space complexity is fairly easy to figure out in this case. So that basically the end of the second last example of dynamic programming, and we look at the next problem. Yes. So now remember, we're not just doing one matrix multiplication. Okay, that was doing just one matrix multiplication. The complexity of this particular problem was actually how many parenthesizations do we need to do, and this was omega of 2 to the power n. If you want to find an exhaustive solution to which set of possible parenthesizations can take, the number of different types of parenthesizations is exponential. Okay. So, so being able to do that in n cube is a fantastic reduction from 2 to the power n. Okay. So, I mean, dynamic programming is terrific for really difficult problems. Reductions in complexity it gives you is absolutely amazing. So now let's take a look at, unless there are any questions on the matrix chain multiplication, let's take a look at another somewhat similar, but each one of these problems is unique as well. Okay. And you can sort of see that we've seen at least 4, maybe 5 different examples of dynamic programming so far, including some graph problems. We looked at the rod cutting problem, the LCS problem, and the matrix chain. So each one of them are similar and some uniqueness as well. Okay, and that's going to be true in this last case as well. That the real challenge in all of these is to make sure that you have the methodology correct. Okay, you attack the problem in, you know how to attack the problem. And secondly, can you figure out the difficult questions, which is, first most difficult question is, does it have an optimal substructure? Okay, and the second question is, does it have overlapping subproblems? And then, of course, be able to use the optimal substructure to write down a recursive equation and then do memoization. So, what is the the optimal binary? Let's take a look at and remind ourselves what is a binary search tree. Okay, so I hope everybody remembers that. So let's say you have keys C, J, and Z. Okay, and you are creating binary search trees with them. So it depends on how you order them. You can come up with at least 3 possible trees. Okay, so you could have Z, J, and C. Remember that this is a binary search tree. So C will be before J. So if you're doing a search for C, you'll say, well, is C comes in alphabetically before Z or not? And yes, so you go down the left path, and it's comes in before J, so you keep going down. If you have this particular structure, then this is clearly optimal. I mean, we always know that if you can minimize height of a binary search tree, that generally gives you the best result. And these two are clearly not optimal, simply because they're in fact the worst cases, because you have all of these, the number of comparisons that you need to do is going to be linear in n, versus it's going to be log of n in this case because it's a balanced BST, right? And we went through a lot of effort to learn algorithms such as AVL and RBTs to be able to figure out how to balance these BSTs, okay? So clearly the solution over here for an optimal binary search tree is obvious that you would want to use this particular solution, right? So why do we need to buy a whole DP algorithm for that? That is in the following scenario, okay? So this is a slightly modification of the problem, which says, what if the frequency of search is not uniform? Okay, now we know that Z, if for example, you're searching for names starting with Z, probability of a name starting with Z is generally lower than the probability of a name starting with C. And probably name starting with J is somewhere in the middle. Okay, so depending on the past results that you have, you may want to assign certain probabilities to each one of these searches. Okay, so in other words, this table is saying that the probability, are we going back to probability? Okay, interesting combination of probability, and can't get away from probability, unfortunately. Okay, so we're saying that, but this is not a very complex probability problem. Okay. So we're saying that the probability of searching for a name starting with C or just the letter C is 60%. And there are only 3 letters in this table. Then the probability of C is 60%, J is 30%, and Z is 10%. So in other words, when you sum these up, it comes to 100%. Okay. Now, you might say, well, what if I search for the letter B? B is not there, and there's a certain probability that. So that's a slightly complex version of the same problem, which is actually what is done in CLRS. Okay, but that additional complexity doesn't give you a lot of value addition in terms of having an intuitive understanding of the problem. So I'm going to drop that for the initial portion of this discussion, and we're going to assume that you're only looking for elements which are actually in the data structure. Okay, so we're only going to look for C, J, or Z. Not going to look for all the other alphabets. So the sum of these is clearly has to be 100%. The question now is, in this particular scenario, can you venture to guess which particular binary search tree of these 3 would be optimal? Would probably be better than the other. So now you're saying, no, they have different weights. So maybe the one which seems to be the optimal may not be the most optimal, because now you're searching for it. You know, C search a lot more than Z. So how could you, just by intuition, can you guess a solution? Yes. The one on the right, and can you sort of explain your reasoning? Yeah. And so naturally, it seems like this would be the right solution, because we're saying that even though this has a greater height, okay, the height of this is 2 versus the height of this is 1. All right. This seems to be balanced, and this seems to be completely unbalanced, right? But the fact that C is being searched for 60% of the time, it seems like makes sense to see right on the top, okay? Because if you think about the number of comparisons that you'd have to make, or how many nodes you'd have to examine to be able to make a decision for 60% of the time, it would be just one examination. Okay, you look at the first node and you'd say, well, in 60% of the time, it will only require examining 1 node. Okay, another 30% of the time, you'd require examining 2 nodes, right? The first node and then the second node, and you'd come to J. And only 10% of the time would you require to examine 3 nodes. Okay, first node, and Z is not there, so you look on the right, you keep on going until you get to the bottom, and that will take you examining 3 nodes. Okay, So the question is, what is expected number of searches? Okay, so how would you calculate the expected number? Now, this is again going back to your basic probability. How does one calculate the expected number, expectation of a random variable? RVs, great memories, huh? How do we calculate the expected value of a random variable? Yes? Yeah, so take the value times the probability of that occurring. Okay, it's a very simple equation. So you basically say, well, C requires, so we're calculating the expected number of examinations. Okay, so in the first case for C, you'll only require examining one node, and the chance of that is 0.6. The second case is when you're looking for J, you have two nodes to examine, first and second, multiplied by 0.3. This happens 30% of the time. And in this case, you have to examine three nodes, and the chance of that is 0.1. Okay, and then you sum this all up and you get a number. Okay, so that's what I've done over here. We're defining the cost of the tree, C of t, as the expected number of nodes to be examined. Okay, and I'm sort of giving you a few terminologies because these will come in handy later on. So we're defining K to be K1, K2. These are the keys, and you have n distinct keys. All right, and K1 is less than K2 is less than Kn. In other words, either you have an alphabetical sorting or some other kind of sorting. And we're saying P sub I is the probability that a search is for Ki. Okay, and we're saying T is some binary of K, one of the possibly large number of trees that you could have. And the cost of this particular tree is going to be the expected number of nodes to be examined. Okay, and so in this particular example, K is shown to be C, J, and Z. These are the probabilities that we have. Okay, we've got a matrix of probabilities. And now we're calculating this, and we're essentially saying, well, the depth of C is 2, the depth of J is 1, and the depth of Z is 0. Okay, so there's a difference between depth and the number of comparisons. So the contribution over here is going to be 3 times 0.6, right? That is 3 times 0.6. So this was the case where you have a different scenario. So this is the first case that I'm looking at now. Okay, so C requires 1, 2, and 3 nodes to be examined, which is basically the depth plus 1. Okay, so 3 times 0.6. This is J is at a depth of 1. And so the number of comparisons is depth plus 1, which is 2. 2 times 0.3. And Z is at a depth of 0. So it's depth plus 1. That's 1 times 0.1. And if you sum those up, you should be able to get the following number, which is 2.5. Okay, so 2.5 is the expected number of nodes that have to be examined on average. Okay, given that the distribution is given to you. Now, if you're trying to find an optimal binary search tree, you would clearly need to say, well, we need to minimize this expected cost, right? You're going to try to minimize this expected cost over all possible binary search trees that can be produced out of n keys. Okay. So here's the equation for this, which is basically saying the depth plus 1, which is what we did over here. Okay. This is 3 times the depth plus 1 times the probability of searching for this particular key. Okay. So now there could be, of course, a whole bunch of binary search trees. So we need to be able to say, well, is this the best? Is this the best? Clearly not. Well, we had a suggestion that this seemed to be the best, so let's calculate this. And I'm not going to do that manually. You can see that the depth is 0, so it's going to be 1 times 0.6. This is going to be 2 times 0.3, that's 0.6. It's going to be 3 times 0.1, which is 0.3. And if you add them up, this has an average number of nodes that have to be examined is 1.5 versus 2.5. Okay, so this clearly is better than this. And for this particular case, which seemed to be optimal initially because it was balanced, however, the number of comparisons is going to be 1.7. The number of nodes that have to be examined is 1.7. So this seems to be the optimal solution, right? Now the question is, first question we always ask is, can we do an exhaustive search and see, well, can we just do it exhaustively and see, well, what is the complexity of doing an exhaustive search? So the question is, what is the number of possible binary search trees with n nodes? Okay, so if you have n nodes, how many different binary search trees can you create of that? Is there a simple solution to this number? For n is equal to 3, is this number 3? Are those the 3 possible binary search trees? And the hint is no, it's not. We're missing out some. Can you guess which ones we're missing out? Yeah. Sorry. You did have an answer, right? You're retracting your answer. Yeah. So if C is on the top, there are 2 possibilities, right? So JZ, or it could be ZJ. Okay, and those are both binary search trees. It's just that the order in which they came was probably C first, and then Z, and then J. So if that comes in, then you put in C first, and then say, well, Z is going to be on the right of C. And then you're going to say, well, J has to be on the right of C, but on the left of Z. So this would be JO here. Okay, so you can see that these two are similar in that the root is the same, but the subtree is different. Okay, so the subtree over here is a variation. So is there another subtree that we're missing out? Yeah. Yes. So only the insertion order is different, but though that is potentially another binary search tree whose cost has to be evaluated. And it will be different, right? Because the location of Z and J has been reversed. Okay, and so the depths have changed. And so the probabilities have to be multiplied by a different depth. Okay, so are we missing out one more BST? Which one are we missing out? Clearly with Z at the top, there is, yes, Jane? Yeah, so Z, and then C, and then J, right? So you can see that we are missing out on 2, and there's a way to calculate this. And this is called Catalan numbers. Okay, so this is done in chapter 12 of the book, which we have skipped. That's the data structures part. But I think this is not really something that one proves. It's something that is a little tricky to find out. But these are Catalan numbers, and they are basically 2nc divided by n plus 1, which is basically the following number, 2n factorial divided by n plus 1 factorial divided by n factorial. So if you calculate that for 3, you have 6 factorial divided by 4 factorial divided by 3 factorial, which comes out to be 5. Okay, and so we saw that, yes, there are a total of 5 possible BSTs. This is not a simple number to calculate because it's not all possible permutations, for example, will result in a separate, a unique BST. Okay, so what seems to be the complexity of this equation? Is this a polynomial equation, or is this an exponential equation? What's the complexity of an exhaustive search going to be? Any thoughts? Should give you some hints. Is it going to be polynomial, or when you say exponential, that means that n is appearing some alpha to the power of n, right? As opposed to n to the power of some alpha or beta. So these are polynomial equations. These are exponential equations. So if you have a 2n factorial, does anybody remember what the equation for that is? We did do this. You remember Mr. Sterling? Yeah, we did do this, right? Yeah, somewhere back in the memory. So this is definitely an exponential solution, okay? And it's a pretty bad solution. So yeah, before we get to that, let's take a look at if we try to solve for all the 5 possible cases. It turns out that some of them do have matching values. These 2 cases, these 2 have the same number of the same optimal solution, and this one turns out still to be the best. Okay, but an exhaustive solution is clearly not very useful, because as you can see, when you have n is equal to 4, you have a total of 14 possible solutions if you calculate this. And as you get n becomes larger and larger, the complexity of this is exponential. In fact, the lower bound is known to be given by this horrendous looking equation, which is 4 to the power n divided by n to the power 3.2. I don't know how they got that, but that's supposed to be a lower bound on this equation. Okay. So so obviously we're looking for a programming solution which can hopefully give us a polynomial time solution to this problem. Okay, maybe n to the power 3 or n. So the first question, of course, our usual favorite question is does it have an optimal substructure? Now I'm going to wait until somebody gives me the right answer for this. How do we go about figuring out what's the strategy to be able to figure out whether it has an optimal substructure or not? Just the strategy, not this actual solution. How would we? Yes, Tomas. Very good. Yeah. So we start by assuming that there is some optimal substructure, and then the next step would be? Yeah, the first part, right? We're going to say that it should be optimal. If it does have optimal substructure, then we're going to assume that there is an optimal solution. We're going to say, well, let's take a smaller problem within that, some subcomponent or a subtree, and we're going to say, well, if there is optimal substructure, then that smaller problem should also be optimal. And then how do we prove that is the case? Our favorite technique. Yes. Sorry. Cut and paste and show a contradiction. So now, can somebody now go the one step forward and tell me how should we actually go about doing that with this particular problem? You see, every problem is unique, and this is the toughest part: is to be able to figure out how do you actually tackle the optimal substructure of this problem. How would you even define an optimal substructure? Maybe it's completely obvious to some of you, but it may not be. Okay. Yes, that's yeah. Excellent. Okay, I thought it was tricky, but I guess you guys are getting really proficient at DP problems. So I hope everybody got what last year, right? said is that you take an optimal solution. So let's make a solution which we know is optimal. Okay, so we know that this particular solution is optimal. Okay? That makes it easier for us to visualize the solution. So let's call this tree T. Okay, and then we're going to say, well, let's take a look at a subtree, which I'm going to call T1. And we're going to say, well, if it does have optimal substructure, then T1 will also be an optimal solution. Okay. And now to be able to prove that, we're going to, as you suggested, is to take another substructure, another subtree, and let's say, well, what if that subtree has a better solution? Okay. We're going to cut this out, cut T1 out, replace it with another solution, and see if it will be a contradiction. Okay, so which of these solutions should we pick to replace T1? To replace proof, right? So I've got the entire T, and I've got T1, and I'm going to try to replace it with another subtree and try to show there's a contradiction. Yes. Yeah, very good. So what we could do is we could take T1 prime, all right, because these two are the same. The root node is the same in both cases, see, all right? And we could do is we could cut this out and replace it in the original tree, and then that tree would become T prime. Okay, and so then what we need to show is that the optimal solution for T prime, if T1 prime, if the cost of T1 prime, this is how I'm going to indicate it, the cost of T1 prime is actually lower than, so is more optimal. If cost of T1 prime is less than the cost of T1, then that implies that the cost of T is of T prime is less than the cost of T. Okay. Does everybody follow this reasoning? We're saying that we've taken this structure out, we've replaced it with this. The new structure is called T prime. And if this is true, if the cost of T1 prime, if this has lower cost as compared to this, then the big problem, the bigger cost is actually going to be the CT prime is also going to be of a lower cost. And that would be a contradiction, right? Because we've already said that the cost of T is optimal, and you can't have another tree which has a lower cost. Okay, so that's going to be our strategy. So let's just do that. So here is what I've just shown you, is that here is C, and we've taken T1, and now we're going to do the proof. Okay, so I've taken T1 prime to be, as was suggested, to be this other, in which C is the same, but we have ZJ changed to be, JZ to be replaced by ZJ, okay, in a different order. So this is our example problem, and we're trying to assume that T1 is not optimal, that this is not optimal, and that some T1 prime is optimal. Okay, cut T1 out of T, paste in T1 prime, forming T prime. So we formed T prime by taking this guy out and replacing it with T1 prime. And this whole tree is now called T prime. And then we're saying basically that then T prime would have a lower cost than T, which is a contradiction. So is that sufficient proof? Or we, as in the earlier case, remember, we sort of jumping, maybe making a statement which maybe requires a little bit more analysis. You think this requires a little bit more? Is it completely obvious that if we replaced that this subproblem, if this had a lower cost, then this bigger problem would also have a lower cost. Is that completely obvious? Again, maybe it is to some of you, but it doesn't seem to be that trivial, because we really haven't shown what is the relationship of the overall cost of T, let's say the cost of T over here, and the cost of T1, right? Or the cost of T prime, how does that compare to the cost of T1 prime? In other words, if you think back to a shortest distance or a minimum spanning tree, then it's a very simple summation, right? It's a sum of this plus the sum of this. That's the total cost of a minimum spanning tree. But in this case, it may not be so obvious. It may not be a simple summation. So we need to have some equation which relates the cost of T and the cost of a subtree. Yes. So let's put this over here. So I'm going to say PC. So can you repeat your answer? Of the cost of the subtree, so J, Z times so that's going to be the cost of T1. Okay, so very good. Can everybody see that? And can you sort of explain your rationalization? So it may be obvious, but just state it again. So you're saying that the property, that the cost of T is basically the probability of C times its depth, which is 1, because it's right at the top, okay? Plus the probability that this entire thing happens, okay, PJZ times the cost of T1. And the cost of T1 is assuming that it is at the root level. Is that what you're assuming? That it's not below, but it's actually right at the top. Okay, so that's excellent. And for those of you who are still confused, let me go through this in a little bit more detail. Okay. We do have some time. So, so basically, what we're basically saying is that we need to have a relationship between cost of T and the cost of T1, what we're trying to evaluate. And let's do this in the following manner. Okay, so which is, I think, exactly what Yuvraj just mentioned. Let's figure out the cost, and I'm going to define the following. Ci, comma j is going to be the expected cost of searching a BST from Ki through j. Okay, in other words, the cost for going from K1 to K3 is represented by C1, comma 3. Okay, so this can be represented by the probability of K1, which is P1. Each one of these has a probability P2 and P3. Okay, remember this is going back to this definition over here where we said that we have these probabilities Pi, the probability that a search is for Ki. Okay. So the cost of C13 is the probability of K1 happening times the depth plus 1, which is 1, plus P2 times 2, right? Because you have to examine 2 nodes, plus P3 times 3. Right? So far, so good. Now, we're going to now separate out the subtree and just look at the subtree. Okay, so what's the cost of 2, 3? Well, that's basically the probability of 2, P2 happening, P2 and P3. So P2 times now 1, because now we're assuming that the subtree is right at the top. We're just looking at that subtree. Okay, so P2 times 1 plus P3 times 2. Okay. Now the question is, can we combine these two equations? Which is what you did. But let's see if somebody else can see that. Equations. Can we write C13 in terms of C23 as a function of that? This requires a little bit of manipulation. So you notice that you have P2 times 1 over here and P3 times 2 over here. Okay, so these have one addition because of the height. We change the height. So over here, the numbers are being multiplied by 1 more. Okay, so we could rewrite this as P1 plus P2 plus P3 times 2 plus another P2 plus another P3. Okay, so now you have P3 times 3 and P2 times 2. Okay, so these two are now equal. And now what you can see is that P2 plus P3 times 2 is exactly this portion. So in other words, we could write this entire equation C13 as P1 plus the cost of 2, 3 plus, and this is essentially what Yuvraj said is the probability of this particular scenario happening. Okay, either J or Z being picked. Okay, so P2 plus P3 is essentially saying what is the probability that either K2, the second key, or the third key was picked. Okay, and we're going to use a shorthand notation for this. This is going to be written as W2 comma 3. Okay, the weight of keys 2 and 3. So we can write this as weights of T2 comma 3, W2 and 3. Okay. So we do have a few more minutes left, and let's just complete this. Now let's take a look at an alternate structure, right? So we've got an equation for this, which is basically this exactly what I've done over here. So we've got this equation C1 comma 3, which is basically C2 3, okay, which is the cost of the subtree, plus a weight, which I've defined as P2 plus P3. Okay. So now let's take a look at what happens if we look at the alternate T prime. Do we get a similar equation? And in fact, if you just go through these steps, you'll see that you get exactly the same equation again, right? So in other words, regardless of the structure of the subtree, you can write the equation as follows. C13 is going to be the cost of the root that's been picked, plus the cost of the subtree, okay, plus the probability that that subtree takes, that one of those elements of the subtree takes place. Okay, so now we've got a nice little equation which is going to be true in both cases. So this particular equation is true regardless of whether you're looking at T1 or you're looking at T1 prime. Okay, so either you pick T1 over here or you pick T1 prime. In both cases, this particular equation is true. Now, what's interesting is that regardless of whether you have T1 or T1 prime, the weight of W23 remains the same, right? Because we're simply saying what is the probability that either J or Z took place, and that is independent of which order you put J and Z, whether it's ZJ or JZ, okay? So the weight of W23 remains the same. So this portion remains the same. This portion remains the same, okay? So the cost of 1 to 3 now is simply a function of the cost of the subtree, okay? So if the cost of the subtree is smaller, then the cost of the bigger tree is also going to be smaller, all right? So essentially, this particular equation, which we said, how can we be sure of this? We've essentially confirmed this particular equation. Okay, so this is confirmed. So now this equation can, in more general ways, be written as follows. Okay, but let me skip over this for right now. Let me just show you, because we do have a few more minutes. At the beginning, I mentioned that CLRS shows you a more general solution. Okay, and here's a more general problem. Okay, here's the more general problem. So here we're going to be saying that these are the keys. Okay, but there's a possibility that you're searching for a number or an alphabet or an element which is not there as one of the keys. Okay, so if you depict it in the following way, let's say that here is a binary search tree. These are the keys. Okay, but there's a possibility that you may be looking for some value which is less than K1. Okay, and that might have a certain probability as well. So that those are probabilities of an unsuccessful search. Okay, if you hit one of these guys, then that's a successful search. But if you hit one of these leaves at the bottom, then that represents an unsuccessful search. Okay, and so those may also have certain probability weights. Right, you don't always find something. You don't always find what you're looking for in the binary search tree. So this is a more general problem where we're basically saying that these are the distinct N keys which are present, and these are the dummy keys, okay? And these are essentially all the leaves. And we're going to represent the probability P to represent the probabilities of the actual keys. And the dummies are going to be represented by the probabilities Q. Okay, so this is going to be Q0 and so on. And so now the sum of P sub I and Q sub I, if you sum them over the entire thing, that is going to be equal to 1. Okay, so this is a slightly more complex version of the same problem, but essentially it has the same intuitive concepts behind it.